You know, every single day, maybe dozens of times, invisible algorithms are making decisions about you. They're drawing a line in the sand and putting you on one side or the other. So, how do they decide where that line goes? And maybe more importantly, who tells them where to draw it?
It turns out that for a machine, a lot of life's most complicated questions really just boil down to a simple binary choice.
It's a world of yes or no.
You see this one all the time, right? Your inbox is basically a battleground where an algorithm decides for every single message, is this junk or is this important? That's it, a simple yes/no call.
Okay, now the stakes get a lot higher. I mean, this decision can change someone's life. It can determine if you buy a house or get to start a business. But at the end of the day, for the algorithm, the outcome is still binary. Approved or denied.
And here the stakes are about as high as they get. This is the yes or no question that we're really going to focus on, where the line an algorithm draws can literally be a matter of life and death.
But here's the twist. It's a big one. These incredibly powerful machine learning models that answer our questions, they don't actually spit out a simple yes or no. What they give us is something much fuzzier, a probability.
So, the model does its thing, it crunches the data, and it spits out a number, something like this, 0.73. Okay, so what do we do with that? Is a 73% chance of being sick a yes, or is it still a no? What is anyone supposed to do with just a number?
This is the really crucial step. We need some kind of tool that can take that uncertain probability and turn it into a concrete, actual decision we can act on.
And that tool has a name. It's called a threshold. You should just think of it as the deciding line. It's where we, the humans, literally draw a line in the sand. We say anything above this line we're going to treat as a yes. Anything below it we'll treat as a no.
Now, the most common sort of out-of-the-box threshold is 0.5. And it makes sense, right? If the probability is more than 50%, let's call it a yes. If it's less, we'll call it a no. It's just a simple, clean split right down the middle.
And if you only remember one thing, let it be this. That 0.5 line isn't a mathematical rule. It's not a law of physics. It is a choice, a human choice, that has massive, massive consequences.
So let's see how this choice actually plays out in that high-stakes medical scenario we were talking about. This is where all the theory gets very, very real.
See, in medicine, not all mistakes are created equal. Telling a healthy person they might need a few more tests, well, that's an inconvenience. But telling a sick person that they're perfectly fine, missing their disease entirely, that is a catastrophe. We call that a false negative. Because we know the cost of a missed case is so devastating, we just can't stick with that default 0.5 threshold. The risk is way too high. So we make a deliberate choice. We move the line.
So instead of 0.5, a medical screening model might have its threshold set way down to something like 0.2. What that means is now any patient with just a 20% probability of having the disease gets flagged. We're casting a much, much wider net. And this shows the trade-off perfectly. By lowering that threshold, we know for a fact we're going to get more false alarms, more healthy people flagged for follow-up tests. But we accept that cost because the alternative, missing even one sick person, is a price we are just not willing to pay. This whole situation shows us that just accuracy isn't a very good way to measure if our model is working. I mean, think about it. A model that just predicted healthy for everyone with a rare disease would be 99% accurate, but it would be totally useless. We need better tools to measure what really matters.
And this is that tool. It's called a confusion matrix, and it just organizes the 4 possible outcomes. We can be right, a true positive or a true negative. Or we can be wrong in 2 very different ways, the false alarm and the one we really worry about in medicine, the missed case.
And from that matrix, we get 2 really powerful ways to measure performance. Precision asks, of all the times we raised an alarm, how often were we actually right? That's all about the quality of our predictions. But then there's recall. It asks, of all the sick people that were actually out there, how many did our model manage to find? That's all about quantity.
And here is where it all clicks into place. For cancer screening, we have to maximize recall. We need to find every single possible case, even if it means more false alarms. We sacrifice precision. But for spam filtering, it's the opposite. We have to maximize precision. We absolutely cannot afford for a critical email to get lost in the spam folder. The real-world context tells us what to prioritize. So let's zoom out for a second and really lock in the big idea here, because this isn't just about numbers and code. It's about something much more fundamental.
The crucial point is this: the threshold, that simple cutoff number, is the exact point where our human values get programmed right into the machine. It's how we tell the algorithm what we care about most and what kinds of mistakes we fear the most.
That number is the human in the machine. It's us making a deliberate judgment call. It represents our policy decision about which mistakes are acceptable and which ones are absolutely not. It's where we decide what kind of world we're willing to live with.
And all of this leaves us with one final and pretty profound question. As these automated systems make more and more of these critical decisions about our health, our money, and our lives, who should be the one to decide where that line gets drawn?